continue. So we're having a look at, guys, further expectation and variance. So just to get started, here's a quick one I want you to try for me. X and its probability. So x could be 1, 2 or 3, and we'll keep the probability 1 over 3, 1 over 3, 1 over 3. I would like you to get, for me, expected value of x and the variance of x. Now, well, I think this can be worked out pretty quickly to be 2. Just give me the variance, please, on your calculator. Sounds believable. It's going to be 1/3 plus 4/3 is 5/3 plus 9/3, isn't it? So that's 14/3 minus 4, which is 12/3. 2 over 3, yep. 2 over 3. Oh, Dasha, you did spend an hour doing it, no? It's 1 squared times 1 over 3 plus 2 squared times 1 over 3 plus 3 squared times 1 over 3 minus 2 squared. Yeah? Is that okay, guys? Yeah? Now, here's another one for you to try. 2x plus 1. So, well, it's going to be nearly the same. Probability 1 over 3, 1 over 3, 1 over 3. So this would be 3, 5, and 7. So calculate that, please. I think, again, you'll find quite quickly that this will be 5. I'm not sure, you'll have to check. I wonder if you get 8 over 3.
Yeah.
Yes?
Yeah.
Now, you might have guessed this or figured this out, but if you know this, then you can skip the calculation and quite quickly go to the answer. It's not too surprising to see that the expected value of 2x plus 1 is the same thing as twice the expected value of x plus 1, like this. What was this originally? 2. So this does work out to be 5. But you notice that this trick doesn't work here. This is not twice the variance of x plus 1. Because if it was, what should it have been? 4 over 3, 7 over 3, I think. And it's not. So we do have one shortcut we can use. If you want to calculate the expected value of ax plus b, and let's say you already know the expected value of x, then this would be a expected value of x plus b. Which kind of makes sense. In a way, you already used this idea previously. Remember when we said, oh, per turn you lose 90 cents. And what would happen if you played 10 times? Then you would lose 9 euros, isn't it? 90 cents times 10. So, in our mind, we're already quite happy saying that this is linear. I think this is intuitive. But what's not obvious is what is the rule if you want to calculate the variance of ax plus b. It's not actually the same rule as this. And I wonder if anybody has seen the rule before, or they know it. No. It works like this. It's a squared variance of x. No plus b. So in fact, the plus b has no effect on the variance. So for example, that would mean if I had this table, 1, 2, 3, 1 over 3, 1 over 3, 1 over 3, and this table, x plus 1, so that's 2, 3, and 4. I know for a fact that the variance here and the variance here will be the same by using this rule. Because the only difference here is this is variance of x and this is variance of x plus 1. But according to this rule, the plus 1 doesn't matter. So you don't need to, but you could calculate and you'd see the variance would be the same for both. The expected value won't be the same. The expected value here, you could work it out, it works out to be 2. And likewise, the expected value here should be 2 plus 1. Should work out to be 3. So it's nice you have these shortcuts here. Let's actually do a proper example now. So you definitely need these rules. Can I scroll down? Yeah? Not yet. Can I scroll down? Yeah? Another thing that's nice about expectation and variance is it can work when you combine two games. So for example, suppose you have game X and then this followed by, let's say, game Y, and you play the two games, and you want to know, okay, what's the expected value of my outcome from game X, then I play game Y. Well, it's nice to know that it's the expected value of game X plus the expected value of game Y. So let's imagine, for example, I expect to win €3 from game X and I expect to lose €1 from game Y. Then what do I expect to gain from playing X plus Y, the two games? Yeah, should be 2. That's all nice and straightforward, isn't it? And the same thing applies for variance. Variance of X plus game X plus Y is equal to variance of X plus variance of Y. So that's another nice feature as well. So games combine easily together. Expectation and variance adds when adding games. Okay, I'll do an example now when you're ready. Can I scroll down? Yes? No? Yes? Okay. Okay. Let's say expectation of X is 2 and the variance of X is 3. Let's do some calculations. So what's the expected value of X plus 1? 3. What's the variance of X plus 1? 3. 3. What's the expectation of 2x plus 3? What is it? 7. What's the variance of 2x plus 3? No. 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 Again, I said no the first 2 times someone said 4. So, no. 12. Did you? I'm sorry, I misheard you. I thought you said 4. Yes, 12 then. Thank you. Yeah, it's 2 squared. The rule is, if you go back to, is it gone? Oh, I'll just write it down again for you. I'm using this rule here. The variance of ax plus b is equal to a squared variance of x. So here, what is squared? It's 2. This 2 squared times 3. Yeah? Yeah? Okay. And I'll give you this one. It'll take you a minute, but I think some of you will get it. What is the expected value of x squared? And don't say 4. It's not. Because, as Hazza will tell you if he was here right now, this is not equal to this. Right? Yeah, for the same reason that that is not equal to that. And it's definitely impossible to be negative here because of the square. I'll have to calculate it. I'll have to calculate it. I'm hearing 7 or 9 as answers. I think it's going to be, what did you say, David? No, I think it's going to be 7, yeah. Because you can use the rule variance of x is expected value of the x squared minus, and then first you get the expected value, then you square it. So you know what this guy is. What is it? 3. This is the thing you want. And you know what this one is. What is it? 2. Yeah, 2 squared, so 4. So the answer here then is 7 then. Yeah, better write that down. I've seen them do this one in the exam before. Actually, I've seen these 2 in the exam. Okay, did you write that down? Yeah? Let me give you a question, yeah? Let me give you a really tricky one now. No, I'll do a different one now. Okay. Like I said, please make note of D and E because I've seen those ones recently enough in the exam. Can I scroll down? Yep. Okay. So what I'll do, we'll say there's a simple enough little game here. You can flip a coin and let's say if it lands heads, for example, you gain 2, and if it lands tails, you lose 1, for example, and each of these is a half. And then you play this 10 times. What is the expected value of your final position and the variance of your final position? So what I mean is you play the game 10 times, you keep a record of how you did for those 10 times, and you just add up all your scores. Okay. And I want to know at the end of the game what is your final score, your expected final score, and the variance of your final score. Let's see if you can get that. You got it? So, firstly, what's the expected value of x? That will be 2 times a half minus... So that's a half, is it?
Yeah.
And the variance of x would be 4 times a half is 2, plus a half minus a quarter, is it?
Yeah.
So that's 5 quarters minus a quarter. Is it 1? Did I do that right? No, I think I did that wrong, sorry. That's 4 quarters plus 2, 5 quarters, is it? Was that the variance of x? What did you get? No? Is it? 4 times a half is 2, isn't it? 1 times a half is a half. That's, oh, it's not 4 quarters. 8 quarters, 9 quarters. Oh dear. Oh, just tell me, what is it at the end? 2.25?
Yeah.
9 quarters, is it?
Yeah.
Yeah, okay. Right, so what is the expected value at the end? Well, if you play this 10 times, that's the expected value of 10x, isn't it?
Yeah.
Which in this case would be
5.
5. Okay, good. And the variance at the end? Well, that'd be the variance of 10x, which would be 100 times 9 over 4. 25. So that's actually quite large. What's that, like 225, is it, or something? Is it 225?
Yeah.
Did you forget the square?
Yeah.
Okay, you need to be careful with that. Right, write this one down. I'll give you another one. Okay, you got that? Yeah. Scroll down. So, the same as before, except I'm not asking you for the expected value of the final score. Instead, I'm asking for the expected value of the average score. Now, what's the difference? So, what I'm imagining is, last time we added up the 10 scores and kept the total, whereas this time you add up the 10 scores and then divide by 10. Yeah, because you play the game 10 times.
Oh, the average by those scores.
The average of the 10 scores. So imagine you played this game 10 times and you have your 10 scores. Previously we added them all up, and in the end we said we expect to get a total score of 5. Now this time you add up the 10 scores and then divide by 10. So, huh? How could it be the same? Like if I said to you, play this game 10 times and you get 10 different scores and you add up the 10 scores, that will be a different number to adding up the 10 scores and then dividing by 10.
Yeah, but so we need to divide by things. Like,
Think about it. Let's see if you can do it.
Okay.
Oh, you're looking confused. Okay, look, I'll do it for you. So, the average score, what is that? That's you play the game once, twice, etc., over 10, right? That's the expected value of 10x over 10, which is the expected value of x, which we said was, what did we say it was earlier? 0.5. Now that should not be a surprise. Because remember at the very beginning of today, I said the expected value has the same meaning as the long run average. So when I say the expected value is 0.5, what I'm also saying is on average we get 0.5 each time we play. Yeah?
So it's like, it's defined as a long run.
Long run average, yeah. The variance is a little different, but the same idea. Variance of x plus x plus x x over 10. Yes? Which I think actually it works out to be the same, doesn't it? Variance of, well, no, we have to be careful here, to be very careful. This is 1/10 x plus 1/10 x, etc. Yeah. Now remember, we have to be very careful because variance doesn't behave the same way as expectation. So we can at least change this into variance 1/10 x plus variance of 1/10 x, etc. But what happens to the 1/10?
Squared.
It's squared. So this is 1/10 squared times variance of x plus 1/10 squared variance of x.
10 times.
Yeah. This would be 10 over 10 squared
So just
variance of x. So it ends up being
1/100.
variance of x over 10. And what was the variance of x? Originally 2.25. So now it's 0.225. Now, yeah, you better take this one down because this one is quite difficult. No, write it down. Don't write it down. Have you got your notebook there?
Yeah.
Yes, write it down. Don't take a picture. No, write it down now. Everyone else is writing it down. I want to actually show you this last one in action. Oh yeah. While you're writing that down, I'll get it open up over here. What did I say? There's two outcomes. Is it 2 or -1? Was that it?
Yeah.
Was it 2 or -1? And they're equally likely?
Yeah.
Yeah, okay. Can I switch?
No.
Come on, guys, you got it?
No. Who said?
Yeah.
Why, how do you get 10 squared?
Oh, there's 10 variances. They're all the same, so it's just 10 times the variance. You're just adding the same number 10 times. So multiplied by 10. Okay, have you got that? Yeah? Come on. I'm going to switch now to the other computer. Yeah?
Yes.
Okay. So, if you look here, whoops. Right. So, let's say I play the game. Oh, go away.
Can you log just in large?
Yes, yes, yes. Right, so I'm going to imagine I play the game 10 times. So 1, 2, 3, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm pretending I played the game 10 times. So let me calculate the average. Now what did I get? What was my answer? It was 0.5, wasn't it? Wasn't that what I got?
Yeah.
Now, well, I won't get exactly 0.5 here because it's random, but I should get close to it. Oh no, sorry, my mistake. The two outcomes were you could gain 2 or
-1.
-1. Sorry, so some of these should be -1s, not 1s. There we go, that's better. Now you see, I played it 10 times. I think if I was to add in a few more turns, let's say, you see I was getting closer to, what did I say? -0.5, was it? A half, was it? Up to 15. Yeah. There we go. Okay. So you can play the game and then you average all the scores and you got -0.5. But as you can see, you don't get a half every time because there's the randomness to it. Yeah. So let me just go back to 10 of them. 1, 2, 3, 4, 5, 6, 7. Oh, nice. Okay. I don't want to change anything because. Okay, I got lucky twice in a row. Okay, now let's calculate the variance. Okay, it'll go back, I'm sure. The formula for variance, I need to calculate this. Okay, So what's the formula for variance? It's the expected value of x squared, isn't it? Minus this squared. So I should get something like 0.225, I hope. Okay, well you see I'm off because of this. I'm rats.
I know
It was perfect, man.
I know.
Yeah.
Oh, okay. All right. Oh, no. I'm sorry. I'm calculating the variance of x, whereas I should have been calculating the variance of the average. Okay, this is going to get more complicated, so I won't do it. Any other examples I want to do? No, okay, I'll try it. I'll try it. No, I won't. No, will I? No, I won't because it'll confuse you. Yeah, no. I was thinking, oh, I know what I can show them, and then I realised, no. Okay. So I just wanted to show you that, well, I couldn't convince you that this was the same because I realised to do that would be a little bit too complicated. But at least I got to show you that the long run average is 0.5. But you notice even with 10 of them, it actually fluctuated quite a bit. By the way, what do you think would happen if I played the game more times, like say 100 times?
More accurate.
What would you think, guys, would happen to this value here?
we can see.
You can't see.
Oh, just at the... Now it's broken. All right. Well, anyways, in your notes where I said the expected value is 0.5 after 10 plays of the game, you saw in the Excel that the value fluctuated. Yeah. What do you think would happen to its fluctuations if you played the game 100 times and took the average? No, the opposite actually.
Smaller.
The opposite, yeah. The fluctuations would become less. So if you played the game 1,000 times and took the average, each time in Excel I'd expect it to be very close to 0.5 with very little fluctuations away from it. Do you understand what I'm saying? Yeah. And you actually have seen this already when you've done chemistry and biology. The reason you take more measurements and then average the measurements is because the value will stabilize. So what about a student who took 10 measurements versus a student who took 100 measurements?
100.
The 100, there'd be less fluctuations in the value the student could get. Yeah. The same thing happens at the casino. You might think, oh, every day the casino will get a different amount of money because different people are playing and different people win or lose.
Not that much.
But not really. So many people are playing, the fluctuations actually become very small. So it's broken now. So the only thing I needed you to make a note of at the end, perhaps for 1 mark in the exam, I think you would need to know something like the greater the value of n, the less the variance. So if you could just make some note in your notes, the bigger the value of n, the number of times you play, the less the variance. Yeah, you got that? Yeah. The other example where you might see this,
Less the variance.
the less the variance. The other example where you might see this is, you know, when they do surveys, they would say, oh, 50% of people support this or whatever. At the very bottom, they always tell you how many people were in the survey. What would happen if there were more people in the survey? Yeah, less fluctuations, okay? If I asked 100 people what do they think of blank, and then I asked another 100 people what do they think of blank, will I get the exact same answer or a different answer? Different. If I ask 1,000 people what they think of something, and then ask another 1,000 people what they think of something, will I get the same answer? No, but they would be closer together. So less fluctuations. Yeah? Okay, so which ones do I want you to try? So, Carul,
Yeah.
1,
One.
2,
Only.
3, and 4, and 8. 1, 2, 3, 4, 8. You got that? Yes? 1, 2, 3, 4, and 8. Okay. And this is broken, but that's the next teacher's problem, I suppose.